Today, let's dive into DynIBaR, an exciting new AI system from Google that enables photorealistic novel view synthesis from monocular videos of complex dynamic scenes. DynIBaR makes it possible to render novel views from different camera positions and time for a 3D scene capture in a single video. This opens up numerous powerful applications from 3D stabilization to virtual cinematography effects and slow motion generation. Let's start by providing an overview of what DynIBaR is. Some example of it is in action, and how it compares favorably to other state-of-the-art techniques. Then, I'll explain how DynIBaR's neurodynamic image-based rendering approach works at a technical level. Finally, I'll discuss the transformative impact this technology could have on fields ranging from media production to VR and vision research. Let's get started. Overview of DynIBaR. DynIBaR is a groundbreaking novel view synthesis system introduced by researchers at Google that enables photorealistic rendering of new perspectives from monocular video footage of complex dynamic scenes. It represents a major advance in reproducing real-world environments in a controlled and artifact-free manner. The key capabilities of DynIBaR include free viewpoint rendering from a single video camera. Users can synthesize realistic views from any viewpoint, not just original camera position. DynIBaR can handle complex, uncontrolled camera motions like shake, fans, zooms, and rotations. It can model large frame-to-frame motions. DynIBaR can render high-quality novel views for dynamic scenes with moving people, objects, and backgrounds. It explicitly models motions. DynIBaR preserves crisp, detailed textures of hair, fur, foliage, and high-frequency elements. The results avoid blurring or over-smoothing. DynIBaR achieves temporal consistency for objects and background across long videos, resulting in coherent over time. It estimates per-frame depth maps from monocular footage through multi-view analysis. Also factorizes static and dynamic scene elements into a separate representation. It enables advanced video editing applications like 3D stabilization, viewpoint changes, VR content generation, and slow motion effect. The combination of capabilities significantly expand the scope for achievable novel view synthesis for complex real-world video compared to prior state-of-the-art methods. DynIBaR also exceeds the performance of other techniques in depth estimation, handling challenging camera motions, and preserving high-frequency details for dynamic scenes. Its neurodynamic rendering approach sets a new standard for photorealistic novel view generation. Comparing DynIBaR to other methods, to demonstrate the advantage of DynIBaR's image-based approach over other leading techniques, we have some great examples here of it in action on challenging real-world videos. For the application of 3D video stabilization, DynIBaR can generate completely smooth novel views along stabilized camera paths while retaining crisp, clear details on dynamic objects like people. In contrast, depth-based stabilization method often shows jittering artifacts around moving objects along with missing regions in the rendered output. Meanwhile, neuro-rendering techniques like NSFF produce results that are much too blurry due to difficulties in modeling the details of dynamic content. DynIBaR combines strength from both domains of superior stability and clarity. Even when synthesizing novel views from extremely complex camera trajectories like circular dolly motions around dynamic scenes, DynIBaR can render results with proper perspective and parallax. Other methods like DBS create heavily distorted outputs riddled with visual artifacts on such difficult camera movements. When generated novel viewpoints along smooth camera path, DynIBaR preserves fine high-frequency details far better than prior state-of-the-art approach which exhibits noticeable blurring and distortion around people or objects in motion. DynIBaR's intelligent aggregation avoids these issues. Beyond just novel views, DynIBaR also demonstrates advanced depth estimation capabilities. It can produce accurate, temporarily consistent per-frame depth maps from monocular videos by analyzing scene structures across multiple views. This depth maps capture extremely fine details like fur, hair, or foliage, while remaining coherent over time, exceeding the depth estimation performance of other monocular methods. Finally, DynIBaR properly models challenging subtle motions like swaying vegetation and trees thanks to its dual scene representation and motion-aware view blending. As you can see, these examples showcase how DynIBaR pushes the boundaries of realistic novel view synthesis for complex real-world video footage. How DynIBaR's neurodynamic rendering works. Behind the scene, DynIBaR introduces a sophisticated hybrid architecture that combines learned neural 3D scene representation with image-based rendering techniques in an innovative manner. First, DynIBaR encodes the static aspects of the scene using a neural radiance field. This is conditioned on a set of encoded input views from the video. This radiance field compactly represents the larger stationary structures, geometry, and view-dependent effect in the scene using a neural network model. A separate sub-network module then analyzes frame-to-frame pixel displacement and scene flow to explicitly encode only the dynamic elements in the video, like moving people, animals, vehicles, or other objects. This component focuses on extracting features that represents motion boundaries, segmentation masks, and material properties for dynamic entities. A core novel component of DynIBaR is the 4D correspondence volume that establishes correlations between input video frames and output ray directions for novel views. This encodes which source view contain relevant information needed to render each part of the scene from any desired viewpoint and time based on the estimated scene geometry and camera poses. When synthesizing a novel view, DynIBaR intelligently aggregates information from nearby encoded input views under guidance from the 4D correspondence volume. It gathers both static scene features from the radiance field and dynamic scene features from the motion encoding subnetwork. This allows it to reconstruct high-quality photorealistic output rays for each pixels in a novel view while avoiding distortions or artifacts. Essentially, the correspondence volume tells DynIBaR where to effectively sample from across the input video frames in order to reconstruct artifact-free novel views in a neurally guided image-based rendering framework. This hybrid architecture fuses a complementary strength for both compact neural scene representation and image-based rendering to exceed what either approach could achieve in isolation. Broader impacts and applications. With its unprecedented ability to generate photorealistic novel views from monocular videos of complex dynamic scenes, DynIBaR opens up many promising applications across a range of fields. In a world of film, television, and media production, DynIBaR could enable completely new paradigms for visual cinematography and post-production workflow. Filmmakers can leverage DynIBaR to digitally transform ordinary footage into stunning smooth camera moves, dramatically reconstruct scenes from new visual angles, and seamlessly integrate CGI elements and virtual backgrounds, and much more through its novel view synthesis capabilities. This unlocks greater flexibilities and creativity in storytelling process. DynIBaR also makes native 3D immersive experience more accessible. It can be used to synthesize realistic stereoscopic left and right views from conventional 2D video footage. This would allow producers to convert traditional films and shows into 3D without difficult reshoot. VR and AR applications also become more viable using novel views rendered by DynIBaR. For consumer applications, DynIBaR's power can be harnessed to process handheld videos captured by everyday people. It can perform 3D video stabilization to remove jitters, shakes, and unsteady camera motions. Dynamic frame interpolation makes fluid slow motion effects possible. These features greatly enhance creative options when capturing home videos and sharing them on social media. Even fields like robotics, autonomous navigation, and transportation could benefit from DynIBaR's novel view synthesis. Given input vision data from camera onboard self-driving cars or drones, DynIBaR can generate novel photorealistic views from different positions along the traversal path. This augmented training data helps the vehicle better understand complex dynamic environments and improve safety. Beyond these applications, DynIBaR represents a major advance in replicating complex real-world scenes. Its capabilities push forward research frontiers in computer vision, graphics, and video analysis. The technology provides new tools to understand dynamic environments and unlock more lifelike visual experience. DynIBaR points towards a bright future where recreating visual reality is coming even closer to fruition. Technical details and architecture. Under the hood, DynIBaR leverages several key neural network architectural advances to enable its state-of-the-art view synthesis capabilities. The region field representing static scene elements uses the voxel-based MLP network with array marching and hierarchical sampling strategy for efficient novel view rendering. The motion encoding subnetwork employs spatio-temporal 3D CNNs to analyze the optical flow and scene dynamics across video frames. An attention-based blending mechanism aggregates source views features guided by correspondence volume lookups. It uses ray-based geometric tests to handle occlusions and disocclusions. DynIBaR also applies adversarial training techniques to optimize the realism of rendered novel views. The generator network is pit against discriminators network that ensures photorealism. Together, these technical innovations provide a core novel view synthesis framework underpinning DynIBaR's success in modeling complex dynamic scene. In summary, DynIBaR introduces a neurodynamic image-based rendering approach that's synthesizing photorealistic novel views from a long video featuring complex scene dynamics with challenging camera and object motion, where prior methods fails to produce high-quality renderings. It intelligently blends learned neural scene representations with image-based rendering guided by dynamics and geometric analysis. This empowers artifact-free rendering of extremely complex real-world video footage with large camera motions and object dynamics that pose major challenges for other state-of-the-art techniques. DynIBaR unlocks new creative frontiers and feels like media productions through its unprecedented generation of realistic novel views. With capabilities far beyond existing methods, DynIBaR represents revolutionary progress in novel view synthesis technology. Let us know your thoughts on the impact and future of DynIBaR in the comments below by making sure to subscribe to our channel.